Hello everyone, today we'll be talking about algebraic types. And this is quite an interesting topic because in algebra we associate with mathematics, but types we associate with programming. So there's a correlation between mathematics and programming. So first of all, what are types? A type is a collection of objects that have the same property. But for the purpose of this presentation, we're going to pretend they're sets of objects. This isn't exactly true, but it works for our setting. So for an algebra in mathematics, we're going to specifically be focusing on rings. So like the natural numbers. In Wikipedia, there's like a very confusing definition of rings that has all the properties, but we will focus specifically on a few key details of this. So the four main components of the ring are a 0, a 1, addition, and multiplication. And we will be defining all of these using types. And then there's also a whole bunch of theorems about these things that make it a ring. Some of these theorems can include commutativity properties, associativity properties, and distributive properties of these addition and multiplication. So now let's define the four main components of rings. First of all, we can start with the type 0. The type 0 can be referred to in many different ways. Some people call it the empty set. Some people call it void. Some people call it bottom. But for our purposes, we're going to call it 0. It is categorized by having exactly 0 elements. That means it's impossible for something to be of type 0. So if you find something of type 0, something went very wrong. This leads us to proofs about things going very wrong, also known as vacuously true. If we have something of type 0, we have reached a contradiction, so pigs can fly. So let's try proving this. If we have an element of type 0, then pigs can fly. The proof is, first we assume we have an element of type 0. This can't be possible at all, so we've accepted that anything is possible. And if anything is possible, then pigs can fly. Notice that this is not a proof by contradiction, it's a proof by absurdity. We've reached a point in our proof where we've assumed too many things and we've reached an absurd result. So from absurdity, we can conclude anything. Now the type 1 is also pretty simple. It can be referred to as the singleton, or as a unit, or as top, but we will be calling it 1. Noticeably, there's exactly one element of the type 1. We call this element unit, and we will represent it with the open and closed parentheses next to each other. If we have two elements of type 1, because there is only one, then that means that these two elements need to be equal, and they are both equal to unit. So now let's define addition. In normal setting, so you have 3 gummy bears, and you have 2 M&Ms, and you want to add them together. So you have 3 gummy bears and 2 M&Ms. This shows us that when you add two things together in types, you can still figure out where they came from. You can't just mix them together and lose the informational properties about the types. And this is how the natural world works in most kinds of situations with addition. So in addition with types, we want to cleanly specify whether it came from the A or the B when we add them together. So in the addition, we add a special label, L or R, to indicate whether it came from the left or the right. In this case, all the blues from A are marked with L, and all the reds from B are marked with R. Multiplication is also tricky. Let's say you have 2 students and they need 3 different textbooks for their classes. So to supply all these textbooks to the students, you need 6 total books. And the first student will claim the first 3, and the second student will claim the second 3. This leaves us with 2 times 3 is equal to 6, but specifically that we have the pairs of a student matched with a book. so that each book is assigned to a specific student. And this labeling property is what taking the pair of two elements is what the multiplication works. So now we're going to be proving properties about addition. So what does proving a property look like? For this, we'll look at a real-world example of a coin sorting machine. At the top, you're feeding in either a quarter, a dime, or a penny. So you could think of this as the sum type of all of these different possibilities. And the way that the thing runs, if you have a quarter, you put it in bucket 1, dime bucket 2, nickel in bucket 3, and if it's a penny, in bucket 4. So we've established rules for each of the individual cases, and once you have all of the cases met, then you have instructions for the whole sum. So to supply the instructions for the whole sum, you need instructions for each individual case. So now let's think of this in our type version to prove the property of commutativity. To show that A plus B is related to B plus A, you need to convert each one of these things at the top to something at the bottom. So the algorithm that we'll use is to take every labeled L and convert it into a label R, and take every label R and convert it into a label L. So the input type is A plus B, and the instructions are for left, you change it to right, and if you right, you change it to left. And since we've covered each individual case, then we've completed an algorithm for showing that the left side can be converted into the right side. For the identity, we do something similar. We have 0 plus A, noticeably that 0 does not have any elements in it, and we remove all these labels R for A. So what does this look like? We need to consider, for the right case, we have an element of the right side, so we can just drop the label and just give you out the red circle. But for the left side, we've assumed that we had something of type 0, which is impossible. So we just say that pigs can fly and nothing matters at that point. So if you have an input of 0 plus A, the instructions would be, if it's right, you just remove the label, and if it's left, you just say it's absurd, so pigs can fly. Now we can also prove associativity. We will cover one direction of this. If you have the label L, you change it to LL. Label LL, you change it to LR. And label LR, you change it to label R. As an exercise, think about how this actually works, and also consider the opposite direction. How would you convert from the right-hand side to the left-hand side? So far we've defined the natural numbers 0 and 1, but we haven't defined any of the other natural numbers. And for that, I'll show you an interesting representation for as something that I like to think of as number trees. So we will define all of the natural numbers using the addition by adding 1 to each natural number until we've created all of the natural numbers. So noticeably, the number 2 has the two labels, the L and the R, and they both contain units, so it's 1 plus 1. And for 3, you add a new element, L of unit, and keep all the elements from 2, and prepend R in front of all of these elements. This leaves us with one new element, the pink one here, and 2 old elements, resulting in a set of 3 different elements. Now, to do the number 4, you take all of the elements of 3 and you add a new one, the L of unit again, which is the orange one, and then for all the ones that were in 3, you prepend the label R to them. And if you keep repeating this, you can generate all of the natural numbers using this particular method. So let's try imagining this visually instead of using these labels. Number 1 is just units, so it's just the single element. But the number 2 can contain 2 different elements labeled L and R. So you could think of this as like a tree that branches off into 2 different directions, and the leaf nodes represent each of the elements of the set. Then the number 3 takes the rightmost leaf and converts it into 2 more leaves by splitting it into 1 plus 2. This again adds more labels so you can see the R prepended with the L and the R, and adds a new element L unit. We can repeat this process to generate 4, and then we can repeat it again to generate 5, and so on. So now here's an interesting question. We have defined this right tree to be the number 4, but what about this left tree? Are they both the number 4? For the right one, we will say that yes, it is definitionally the number 4. That's how we defined it. But for the left one, we will say that isomorphically, it is the number 4. This means that we can convert the tree on the left by doing conversions on the tree and rearrange it into the tree on the right without losing or replacing any elements. And we can go back and forth between these two different formats. Because of this, we can say that natural numbers are binary trees modulo rearrangement of the leaves. We can decide that the tree on the right is going to represent the natural number 4, and the thing on the left is going to be something that can be converted into the natural number 4 through transformations. So the right is the representative of all the things that are similar. So let's do this conversion and see how it would look like. So here we have the tree 2 plus 2. We see that it's branching off into the left and right, and each subtree of those two is going to be the number 2. But we can further split it up into 1 plus 1 plus 2. Now we can take this tree, and by the associativity property that we had proved before of relabeling these trees, we can convert it into 1 plus 2 plus 2. And here we have the familiar shape of the number 4. So we've created an algorithm here to convert from the isomorphic tree into the representative tree. So now we can prove this algorithm and generate an algorithm for expressing addition of two natural numbers. So the function append, if it's a leaf, then we're done. We just return a plus b. And otherwise, if it's the left-hand side is a branching off of a1 and a2, then we return a1 plus append a2 and b. Now, to prove that this is isomorphic to a plus b, we take each particular case and see what we get. So in the base case, we're done because we've returned a plus b, and that is equal to a plus b. In the else branch, we have that a1 plus, we return a1 plus append a2b, and by induction, we know that this is equal to a1 plus a2 plus b. Then we could do the associativity property, and we know that definitionally that a1 is equal to a is equal to a1 plus a2, so that we end up with the result that it is isomorphic to a plus b. So with this algorithm, we can compute a tree that represents the addition. But what about multiplication? For multiplication, you can think of the algorithm as taking each one of the leaves on the left of the side of the multiplication and converted it into the tree of the right-hand side of the multiplication. So here we see the orange leaves get replaced by the blue trees, resulting in the something isomorphic to 4. So now how do we convert this back into the tree algorithmically? Well, you might not have realized this, but this is something that we learned pretty early on in our mathematical journey, and that is the property of long multiplication. So here you see that the number, to multiply these two really big numbers together, we split it up into a whole bunch of different chunks and represent it as a weird tree of a whole bunch of addition. And then you do all the rearrangement of this tree to result in the actual representation of the number. So here you see that we have we've converted the multiplication algorithm into a series of addition operations, and we have the append function to convert from these additions into the representative number, and that's exactly how long multiplication is set up. You wouldn't have thought of it intuitively that this is actually a rearrangement of the tree that we're creating to convert it into the representative tree. And that is all that I have for today's presentation, but I leave you guys with this question. If we were able to represent long multiplication as this interesting tree transformation within type theory, then what more math can we represent with types? And would it have been easier to learn these graph transformations instead of learning long multiplication, if it's more intuitive to show how this graph changes shape? And thank you for watching.